A hydrogen NMR spectrum has three things we need to always hold in our mind when we analyze it. One, we need to pay attention to the chemical shift of the peak we're analyzing. That's where does it show up in the spectrum, and it tells us something about the chemical environment of those hydrogen atoms. The second thing, we need to pay attention to the integral, or the area underneath the peak. The integral, or the integration of the peak, represents how many hydrogens that peak represents. And the third thing, the one for today's video, is the peak also splits into a pattern, a splitting pattern. It might split into a certain shape. And that shape tells us, if I'm looking at these hydrogens, it tells us how many hydrogens are on the next door carbon atoms. And that's going to be huge for us, so we can figure out what a molecule looks like from its NMR spectrum. Just to remind us about the chemical shifts, the first 7 locations we ought to learn where the different types of hydrogens show up. Our scale is from 0 to 10 or 11 parts per million, and these are the 7 locations, if you remember from our previous video. 0 to 1 are where the regular hydrocarbon hydrogens are. Around 2-ish are the ones next to a carbonyl, or maybe a carbon-carbon double bond next door to them. Around 3-ish, 3 to 4, those are the hydrogens that are on a carbon next door to something special. When we say something special, we mean an oxygen, a nitrogen, a halogen. Around 5 to 6 are hydrogens on regular double bonds. 6 to 7-ish are those hydrogens that are on phenyl rings or aromatic rings. 9 to 10 are aldehyde hydrogens. And 10 to 11 or 12 are hydrogens on carboxylic acids. That's the first 7 locations we just need to memorize right away. Now let's take a quick look at what this molecule might look like. So this molecule has 2 types of hydrogens. These 9 hydrogens are chemically equivalent, and these 3 are equivalent. So these 3 hydrogens are on a carbon next door to a carbonyl. They would show up somewhere around 2. So let's make a peak for those. And that represents 3 hydrogens. And these 9 hydrogens are a couple of carbons away from the carbonyl, so they're regular hydrogens. And they would make a peak 3 times bigger, if I can make it. I'm running off the chart. 9 hydrogens tall. So 3 hydrogens and 9 hydrogens, or the computer might say that's 1 hydrogen to 3 hydrogen ratio. Okay, so that's for this molecule. Let's draw another spectrum and pick a different molecule. So here, let's take a look at a different compound. Oh, let's take a chlorine with an ethyl on it. Ethylchlorine. Chloroethane. Now let's predict where we think the hydrogens would show up. These 3 would be regular hydrogens. And these are next to something special. So these 2 would show up around 3 something. And these 3 would show up around 1. We'll make those a little bigger. 3 hydrogens to 2 hydrogens. So how big they are, the integral tells us how many hydrogens. Where they show up tells us what types of hydrogens we're dealing with. Now, this is not exactly what this spectrum looks like. It's a little more complicated, which can be scary, but it's not really that big of a deal. It's not too hard to understand this. But the good news is, because it gets a little more complicated, the spectrum does, it gives us lots of more information. So let's take a look at what it actually looks like. So we'll redraw the spectrum and I'll show you what this really looks like. So these peaks really aren't single peaks like we've seen in the past. What they really look like, these 2 hydrogens end up looking like this. They still show up at 3, but these are the ones next to chlorine right here. Let's label them A and B. The A protons really look like this. They split into 4 peaks. We call that a quartet. And these 3 hydrogens, the B hydrogens, they split into a triplet. 3 peaks. We call that a triplet. Now again, if you measure the area underneath these peaks, this is a little bit bigger, 3 hydrogens worth, compared to 2 hydrogens worth for the quartet. So here's how they split, and here's the rule for how many peaks they split into. It's the n+1 rule. What you do is you count the number of hydrogens on the carbons next door to the hydrogens we're looking at. So the number of neighboring hydrogens. And then you add 1 to that, and that's how many peaks you split into. So let's come take a look at our A hydrogens, these right here. So these hydrogens right here, we look next door on the chlorine, there are no hydrogens. We look next door on this carbon, there are 3 hydrogens. So 3 hydrogens, 3 plus 1 is 4. We get 4 peaks, a quartet. This peak represents these 3 hydrogens. It's a little bigger. These 3 hydrogens, we look at the neighboring carbon, this one. It has 2 hydrogens on it. We add 1 to that, n+1. It splits into 3 peaks, a triplet. It's that simple. Let's go back the other way. Let's say we don't know what this compound is, and all we have is this spectrum. How could we start to figure out what we have? Well, let's say that somehow we figured out there was a chlorine in this. And we look at this and we're like, okay, it looks like I have 2 different types of hydrogens. I'm seeing 2 different peaks. One of those peaks is 2 hydrogens tall worth of area. The integral is 2 hydrogens. I'm thinking maybe a CH2. And this one is 3 hydrogens tall. I'm thinking methyl, CH3. Now, what are these hydrogens next to? These 3 hydrogens, this methyl, splits into a triplet. So I'm thinking it's next to, if it splits into 3 peaks, it has to be next to 2 hydrogens, next to a CH2. And these 2 hydrogens, since they split into a triplet, or no, a quartet, they have to be next to, let's see, 3 hydrogens to split into a quartet. So next to 3 hydrogens. Well, if this methyl's next to a 2 hydrogen thing, and this CH2 is next to 3 hydrogens, the CH2 and the CH3 are next to each other. And the CH2 is a middle type of thing. It needs 2 bonds on it. CH3s are N types of things. Chlorines are N types of things. I guess I can't have much else but this molecule. And then we can even double check the 2 hydrogen thing. This one is around 3 to 4. Ah, yes, that makes sense because it's next to something special. These 3 hydrogens, which represents this one, these 3 are around 1, so they're more regular. That makes sense because these are farther away from the chlorine. So that's how we think backwards on these problems. That's the n+1 rule. That's the key for this. Count the number of neighboring hydrogens, and that's how many peaks you split into. You add 1, and that's how many peaks you split into. Okay, stick around, and I'll teach you some. I want to do a couple problems with you, just to make sure we've got this down. And then we'll take a look at 2 of the patterns you should really learn, because professors love these patterns the most. They tend to show up on these on your exam more than any others. So those will be at the end of the video. So first, let's do a couple of problems to make sure we've got this down. I just picked 5 different molecules. Let's predict what the splitting patterns would be for these. We might even quickly just think about maybe where they'll show up. So let's think about this problem right here. So we have, looks to me like 4 different types of hydrogens. The CH3, this CH2 is closer to the carbonyl than this CH2. So these are different. And this CH3 is different than this one because this is at the end of a chain. This one's next to the carbonyl. So if I'm guessing where they show up, these hydrogens next to a carbonyl, 2-ish. These hydrogens next to a carbonyl, 2-ish, 2 to 3. These are more regular, maybe around 1. And these are even farther away, maybe a half parts per million, something like that. What are the splitting patterns? These 3 hydrogens that are next to this carbon with 0 hydrogens on it, 0, n plus 1, 0 plus 1, these would be a singlet peak. One singlet peak. These two hydrogens, they're next to a carbon with 0 hydrogens, next to a carbon with 2 hydrogens, so that's 2 total. N plus 1 is a triplet, 3 peaks. Whoop. It actually looks like this. They get bigger and bigger as you go towards the middle and smaller on the sides. These two hydrogens have 2 on this neighbor, 3 on this neighbor, that's 5 total. N plus 1 means it'll split into 6 peaks, a sextet. 1, 2, 3, 4, 5, 6. Notice how they get bigger and bigger and bigger as you go towards the middle. And these 3 hydrogens, the neighbor has, so the peak for this one, the neighbor has 2 hydrogens on it, so it splits into 3, a triplet. And they get bigger as you go into the middle. Okay, so that's what those 4 would look like. What if you get a problem like this? Well, the first thing I would do, since I'm looking at hydrogen NMR, is let's draw in all the hydrogens. So this has 3 hydrogens on that end. This carbon has 3 hydrogens there. This oxygen, of course, has 0 hydrogens. And this carbon would have 2 hydrogens on it. Okay, remember, I'm looking at the hydrogens. So this methyl, the peak for these hydrogens, well, first off, since they're next to an oxygen, next to something special, I would predict they show up around 3 to 4. And if the neighbor is oxygen with 0 hydrogens on it, 0 plus 1, these make 1 peak. We call that a singlet. These 2 hydrogens, they're next to a hydrocarbon and an oxygen. Next to something special. I bet these hydrogens also show up 3 to 4. Let's count the neighboring hydrogens, 0 and 3. N plus 1, 3 plus 1 is 4. So this makes a quartet. Remember, they get bigger as you go to the middle. This is 3 hydrogens worth of area, so it would be pretty big. These would be 2 hydrogens worth of area. These 3, which again will be the same area as this one and bigger than this one. These 3 are next to a regular CH2, regular hydrogens around 1. These 3 that are around 1 have 2 neighbors, 2 neighboring hydrogens. N plus 1, they split into a triplet. This one, CH2, CH2, and a CH3. All right, these hydrogens are next to something special, 3 to 4. More regular, around 1, 1.5 maybe. And these are far away from the chlorine, so these would be probably less than 1. Let's just get into the splitting. These 2, 0 neighbors, 2 neighbors, a triplet. 1, 2, 3, triplet. These 2, 1, 2, 3, 4, 5 neighbors. That's a sextet. 1, 2, 3, 4, 5, 6. And these 3 hydrogens have 2 neighboring hydrogens, so a triplet. Let's draw in the hydrogens on this one. There are 0 hydrogens on my carbonyl, 3 on this methyl, 3 on this methyl. It looks to me like all 6 of these hydrogens are equivalent. They all have 0 neighbors, so it looks like I'd get 1 big singlet. For all 6 of those hydrogens, 1 singlet. And finally, this problem, CH3, CH3, CH3. Carbon with no hydrogens. This is a CH2, oxygen, and CH3. All right, these hydrogens that are all next to an oxygen, something special, these would show up around 3 to 4. That's a different peak than these 2, which would show up around 3 to 4. And I can see all 9 of these hydrogens would be equivalent on the terbutyl. And these are far away from the oxygen, so they show up close to 1. Let's do the splittings. These 3 next to an oxygen with 0 hydrogens on it, singlet. These 2 with an oxygen and a carbon with 0 hydrogens on it, this would also be a singlet. A little smaller than this singlet. And these 9 hydrogens are next to a carbon with 0 hydrogens on it, so they'd be a singlet around 1, and that would be a huge singlet, 9 hydrogens tall to 2 hydrogens tall to area to 3 hydrogens area. All right. So that is just some quick practice. All right, you ready for the cheat code? These are the 2 patterns I would memorize first. Get these in your head because these are the ones that your professor will most likely use. And they are the ethyl pattern and the isopropyl pattern. So if I have a chlorine, CH2, CH3, that's an ethyl. And we've seen this pattern already. It's the triplet quartet pattern. So these would be next to 3 hydrogens, a quartet. And these 3 next to 2 would be a triplet. So whenever you see a triplet and a quartet pattern, triplet, quartet, that's an ethyl. The isopropyl pattern, remember an isopropyl looks like a Y on something. Isopropyl, we have this hydrogen and these 6 are equivalent. These 6 are equivalent and they're different than that 1. These 6 being next to 1 would be a big doublet. And they would be around 1. So you get a big doublet of 6 hydrogens. And this one has 0 neighbors there, 6 neighbors there. It would be around 3 to 4 because it's next to chlorine in this case. But that's just in this case. This one would be next to 6 neighbors, so it's a septet. Let's draw that. 1, 2, 3, 4, 5, 6, 7. And they get bigger and bigger as you go into the middle. So this would be a tiny 1 hydrogen tall septet and a really big 2 hydrogen tall doublet. 6 hydrogen area doublet. That's the cheat code. Those are the 2 patterns that they'll most likely give you. Finally, I've used some terms about these different splitting patterns. I just want to go over real quick just to make sure we're all on the same page. So if you have 1 peak, that's called a singlet. 2 peaks would be equal heights to each other. That's a doublet. 3 peaks. Remember, they keep going up as you get into the center. That's a triplet. 4 peaks. 1, 2, 3, 4 would look like that. That's a quartet. 1, 2, 3, 4, 5. That would be a quintet. 1, 2, 3, 4, 5, 6. That would be a sextet. 1, 2, 3, 4, 5, 6, 7. So it would look like that kind of a pattern. That's a septet. 1, 2, 3, 4, 5, 6, 7, 8. That's an octet. Nonet would be 9. I think you get the idea. A couple things I want you to notice real quick though is the distance between these peaks is the same all the way across. Boom, 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 boom. They have to be the same distance all the way across. We call that the coupling constant. And when they shake hands, they have to be equal all the way across. So how can I use this to my advantage? How about what if say we get a peak that looks something like this? We get 1, 2, 3, 4. And you look at that and you're like, okay, is this a quartet? Or is it 2 doublets? Well, we know that quartets have this pattern, right? 1, 2, 3, 4. This does not look like that pattern at all. So I don't think it's a quartet. And the other thing to notice is the doublet, there's this distance and this distance, but there's a big distance in between there. So this looks like 1 doublet and maybe another doublet. 2 doublets, not a quartet. Okay, I hope that's helpful. Well, if you've been with me from the beginning of this NMR series, that should give you a good understanding of proton NMR and how to interpret a spectrum. But if you're jumping into the middle of this series, may I suggest you click on the link down here and start from the beginning so you can follow along better. And if you want to keep going and learning more, click on this link, and hopefully that'll take you deeper into this subject.